All right, welcome back. Before we get started, somebody asked a very good question on the forum, which I don't know if you've been following. They asked, what is the relationship between artificial intelligence, machine learning, and data mining? This is a very good question. And the answer is, number one, machine learning is a subfield of artificial intelligence. Right? Artificial intelligence is concerned with doing all sorts of things that humans do that machines don't do very well, like problem solving, knowledge representation, reasoning, planning, vision, natural language understanding, speech, multi-agent systems, and machine learning is one of these fields. These days it's probably the biggest of these subfields, and probably also the one with the most impact in industry. So in many ways it's become its own field, but it's really a subdiscipline of AI. As to what's the relationship between machine learning and data mining, it depends on who you ask. If you ask me, it's really about the same thing, and everything that we're going to cover in this class fits equally well under machine learning and data mining. You could really have it. However, there are certain things that people do in machine learning, like say reinforcement learning, that you probably don't see a lot of in data mining. And conversely, there's some stuff in data mining, more like say on the visualization or database side and things like that, that people sometimes call data mining, but we probably wouldn't. Okay? The difference is really largely historical. Machine learning is actually the older term, right? It's a field that's existed for 50 years. Data mining is a term that emerged in industry around the late 80s, early 90s. And in fact, these days there's other terms like predictive analytics and business intelligence and data science and whatnot, all with slightly different slants. But I think for us the main message is there's no real usefulness in making a lot of distinctions between machine learning and data mining, and what we're going to be covering here is very much both. Okay? Number two, as you hopefully have seen, the first assignment is up. As advertised, it's going to consist mainly of implementing a decision tree learner and then applying it to some real clickstream data from an e-commerce company. We await your insights with breathless excitement. So that's most of it. Of course, this is a small-scale version of what you would be doing in the real world, but then nevertheless, it should be useful. We also have some questions about rule induction, which we're going to cover next week. Okay? Anybody have any questions or thoughts before we get into things? All right, let's get going then. So today, we're going to talk about learning decision trees. Decision trees are, according to surveys, consistently the most widely used data mining machine learning algorithm in practice. It's not hard to understand why that's the case. They have a rare combination of being fairly simple to understand and implement. Their output is also quite understandable, and they're not too hard to use. Right? You don't have to tweak a lot of parameters before they return something useful. And they're also pretty scalable. So that combination of things is pretty attractive. For any given application, there might be another method that, if you really put your effort into it, will give you better results. And definitely, there's many other methods that you can use. But certainly, decision trees are, I think, a very good place to start. We will also use them to illustrate some of the issues that actually cut across all these methods, like missing data and overfitting, which are things that you are almost guaranteed to encounter when you do machine learning in practice. So first of all, let us look at what are decision trees and what kind of learning algorithms are decision tree learners. So first of all, decision trees are a variable size hypothesis space. So the size of your decision tree grows with the amount of data that you have. They're, at least in its most basic version, a deterministic representation. So decision tree is something that says, for each example, you're positive or you're negative. And then decision trees actually have both discrete and continuous parameters. The discrete parameters are the choice of attributes to test at each node. And the continuous parameters can be, well, first of all, you might be testing continuous attributes, in which case you need to do with them, like, is the temperature greater than something, for example. Or you could also have, probabilities of, for example, one class versus another at the nodes and at the leaves. Okay? The learning algorithms that we have for decision trees are almost all constructive search algorithms, meaning it's like Lego. We start with one piece, and then we attach another and another and another, and we gradually build potentially very complex structure, one piece at a time. They're typically eager. Again, there are some lazy learning algorithms out there for decision trees, but in the vast majority of cases, people learn decision trees in batch mode, and eagerly meaning, you put a lot of effort into learning your model, on a fixed amount of data, and then you deploy it. So that covers both of those points. So what is a decision tree, first of all? This is generally what we're going to do here, is first understand what the representation is, what it can do, what it can't do, and then once we have figured that out, we go on to what are some of the evaluation measures that we use, and then finally, what kind of search algorithms do we have to optimize those measures and find the best, in this case, decision tree. Okay? So decision tree is a very simple and very old idea, right? You can almost guess what it's going to be just from the name. A decision tree is a tree where in each internal node, you test the value of one feature. For example, you might test whether this patient has a high temperature, or whether they have been in contact with people with this or that, and so on. Okay? So each internal node is going to test one of those things, and then the leaves actually make the class prediction. Yes, this patient probably has malaria or does not. Okay? So here's a small example that we're going to use to illustrate decision tree learning. Suppose you like to play tennis, and there's a friend of yours who you like to invite to play tennis, but sometimes she wants to play, sometimes she doesn't want to play, and you're very shy and afraid of rejection, and so what you would like to do is predict in advance whether she's going to say yes or no, right? And if she says yes, then you invite her, she says yes, and you play, otherwise you save yourself the embarrassment, okay? Now the problem, of course, is that you don't know what goes on in her mind. What you have, though, is, in the past, there's a bunch of days, right, that you asked her to play tennis in, and she said yes or no. So our goal is, from these examples, figure out what is the general rule that decides whether she wants to play tennis or not. Okay? And, let's say we have 4 simple attributes: outlook, which could be sunny, overcast, or rainy, right? Clearly this affects whether you're interested in playing tennis or not. The humidity, which could be high or normal. The temperature, which let's say could also be medium, high, or normal. And the wind, is it strong or weak? Okay. So now let's say that we had our examples and we ran our great decision tree learning algorithm on this. This is actually a small enough problem that you could even do it by hand. And let's say you get a decision tree like this one here. Okay. So how does this work? Okay. Let's say that the attribute at the root is outlook, right? So what that means is that the first thing that you do today when you wake up, when you want to decide whether to call your friend or not, is check the outlook. Okay? And for example, what happens if the outlook is overcast? Looking at this tree.
Let's play tennis.
Exactly. The output is overcast, that decides it. That's enough for your friend to want to play tennis, so we're done. Right? Things end right there. On the other hand, let's say that the outlook is sunny. Then what happens?
Check humidity.
Then you have to check humidity. Because guess what? If the day is sunny and the humidity is high, it's kind of uncomfortable for playing tennis. Okay. On the other hand, if it's sunny but the humidity is low, well then sure, we can still play tennis. Okay? And so on. If it's rainy, then maybe you need to check the wind. If it's rainy but not windy, okay. If it's rainy and windy, it's going to be too unpleasant. Okay? Notice that we actually ignore temperature. It turns out, and it often will, in practice, in real examples, that some of the features that you have collected are actually not necessary. It could be because they really are irrelevant, or it could be because they're just redundant. For example, what the temperature would tell me is already contained in, the outlook and the humidity. Okay? So you might wind up with a decision tree that doesn't use most of the features, and in fact, that's a good thing. Because the simpler the decision tree is, the better it is, for you to understand and predict. Okay? Any questions about the basic representation? Yeah.
So, which features would you prefer to start with? I mean, in here, the order of features are...
Notice that the order of features matters, right? You want to start with the most informative feature. In fact, one of the nice things about Outlook is that if it's overcast, you're done. Right? So what you want to do is you want to test first the features that most quickly lead you to a conclusion. Because the other thing that happens, we're going to see more of this in a little bit, is that if you start testing a lot of features, the amount of data that you have to test these combinations starts to become, exponentially smaller. Right? So pretty soon you're not really able to tell whether, the next feature is relevant or not. Okay? So one of our preoccupations, of course, is going to be figure out, what is the next attribute that we're going to test and how should we pick it? At the root or at any other node. Okay? More questions? Okay, so next question. Actually, let me not even show you this first. This example that we showed here only has discrete attributes, right? Each attribute only has a small number of discrete values. But in the real world, a lot of attributes have continuous values. Like, for example, temperature is, at least unless you discretize it, a continuous value, right? So the next question is like, what if temperature was relevant here? How should I incorporate continuous values into a decision tree? Any suggestions? What can we do? Obviously, we can't test all of their values, right? Because there's too many, right? We can't have a branch for every possible value of the temperature. That would be crazy. So what can we do?
You can use a range.
You can use a range, exactly. So that's one option. Or you can do something even simpler than using a range, which is kind of like using half a range, which is just use a threshold. Okay? So, for example, here's the decision tree that we had before, but with a threshold on the humidity. If the humidity is above 75%, then we don't play. If it's below 75%, then we do play. Okay? And of course, if you compose these, you will get things like ranges, right? You could later be testing, for example, well, if the humidity was above 75, maybe if it's below, 25, then that's a bad case again. Okay? So there's other ways that you can use, but this is the simplest and by far the most common one. Okay? So the next question